Suppose you have a triangle and you chose one point on this side here, one point on this side here, and one point on the extension of this side here. And we're wondering if this point, and this point lie on a straight line. What's the condition for which this is true? Menelaus' theorem gives us the answer to this question. It states that if these three blue points lie on a straight line, then A divided by B times C divided by D times E divided by F equals 1. And if we know that A divided by B times C divided by D times E divided by F equals 1, then we can conclude that this point, and this point lie on a straight line. You can use the same mnemonic we used for Cheva's theorem to remember Menelaus' theorem. So we start here at one of the vertices of the triangle, and we go A divided by B times C divided by D times E divided by F, and then it equals 1. We reached the point from which we started. Again, we put times at the vertices of the triangle, and we put divided by at the blue points that we need to show that lie on a straight line. Now let's prove Menelaus' theorem. First, suppose that we know that these 3 points lie on a straight line. We're going to prove that this equality holds. Let this area be S1, this area S2, and let this area be S3. Then we know that S1 divided by S2 is A divided by B. S2 divided by S3 is C divided by D, and S3 divided by S1 is E divided by F. And so this expression on the left-hand side transforms to this expression. But this expression equals 1 because S1 cancels out, S3 cancels out, and S2 cancels out. Therefore, this equality always holds. Conversely, let's suppose that we need to prove that this blue point, and this blue point lie on a straight line, and we know that this equality holds. So we know that A divided by B times C divided by D times E divided by F equals 1. Now I'm going to connect this point and this point with a green line and intersect it with this line here at this green point. And then I'm going to mark this distance as D prime and this distance as C prime. I'm going to prove that C equals C prime, and so this point and this point are the same point, which would prove that this point, and this point lie on a straight line. By Menelaus' theorem applied for this blue point, this green point, and this blue point, which we know lie on a straight line, we have that A divided by B times C prime divided by D prime times E divided by F equals 1, which is written here. And now that we have that this equality holds and this equality holds, we can divide one by the other and get C divided by D, which is here, equals C prime divided by D prime, which is here. Because A cancels out, B cancels out, E cancels out, and F also cancels out. We take this equality and we add 1 on both sides. We get that C plus D divided by D equals C prime plus D prime divided by D prime. But C plus D is the length of this segment, and C prime plus D prime is the length of this same segment. Therefore, we can cancel these, and therefore D equals D prime, and therefore this point and this point are the same point, they coincide. And hence, this point, and this point lie on a straight line. Note that there is a second version of Menelaus' theorem where the 3 points lie on the extensions of the sides of the triangle. So this is the triangle, and these points lie outside of the sides themselves, but on their extensions. Then, Menelaus' theorem tells us that the 3 blue points lie on a straight line if and only if A divided by B times C divided by D times E divided by F equals 1. Again, a way to remember this is to put a multiplication sign next to each vertex of the triangle and the division sign next to each blue point. And then we have A divided by B times C divided by D times E divided by F, and we go back where we started. So this equals 1. For the proof, I will first label this point as A, this point B, this point here C, this point D, this point E, and this point F. And now S1 is the area of triangle ADF, so ADF. S2 is the area of triangle BDF, so BDF, this triangle. And S3 is the area of triangle CDF, so this triangle. Then S1 divided by S2 is the area of ADF divided by the area of BDF, which is AD divided by DB, which is A divided by B. Next, S2 divided by S3 would be the area of BDF divided by the area of CDF, which is BF divided by FC, or C divided by D. Finally, S3 divided by S1 is the area of CDF divided by the area of ADF, And so it equals CE divided by EA, or E divided by F. When we're getting these identities, we're assuming that F, E, and D lie on a straight line, of course. If you're skeptical about any of the claims made, just notice that all the three triangles that we've used for the areas have a common side DF. And so the ratios between any two areas would be the ratio between the heights corresponding to the side DF of the corresponding triangles, because each area can be represented as DF times a corresponding height divided by 2. And then each ratio of heights can be related to the corresponding ratio A divided by B, C divided by D, or E divided by F by applying the intercept theorem. And so we got that this side equals this side, because A divided by B equals this ratio, C divided by D equals this ratio, and E divided by F equals this ratio. But S1 cancels out here, S3 cancels out here, and S2 cancels out here. And so this equals 1, which means that this equality always holds. Similarly to how we proved the other version of Menelaus' theorem, when two of the points were inside of the triangle, we can prove the reverse direction in this case. I mean that if we know that this holds, then we can prove that D, E, and F lie on a straight line. Here's the optional problem. Suppose we have a triangle and the three x circles are given. Then these blue points are the tangency points of the x circles with two of the sides of the triangle. We need to prove that this line defined by these two tangency points and this line defined by these two tangency points and this line intersect at one point here. And here's the solution. Let's call the sides of the triangle A, B, and C. Then we know that this length is semiperimeter minus B, this length is semiperimeter minus A, this length is semiperimeter minus C, this length is semiperimeter minus C, this length is semiperimeter minus B, and this length is semiperimeter minus A. Let this line intersect this line at this point, and let this line intersect this line at this point. I'm going to call this distance x and this distance y. I'm going to prove that x equals y. If I prove it, it would mean that this point and this point coincide. Then of course this line, and this line intersect at that point. Let's apply Menelaus' theorem for this triangle and this point, and this point, each of which lies on the extension of one side of the triangle. Then we know that this divided by this times this divided by this times this divided by this equals 1. We know that this is b and this is s minus b, and so this distance here is the semiperimeter s. So we have s divided by s minus b written here times c plus x divided by x, which is written here, times s minus a divided by this segment, which is again the semiperimeter. So this last ratio is written here. And by Menelaus' theorem, this expression equals 1. Now let's apply Menelaus' theorem again for this triangle, but this time for this point, and this point, which we know lie on a straight line. So we have that c plus y divided by y times s minus c divided by s minus b times s minus a divided by s minus c equals 1. So this expression is written here. First of all, let's notice that the s cancels here and s minus c cancels here. So from this equality, we get that c plus x divided by x equals s minus b divided by s minus a. And from this equality, we get that c plus y divided by y equals s minus b divided by s minus a. And therefore, c plus x divided by x equals c plus y divided by y. Subtracting 1 from here and from here, we get that c divided by x equals c divided by y. Canceling the c, we get that x equals y, which is what we had to prove.